So for our last section of this unit, we're going to talk about vectors. So let's review what vectors are first. So remember, a vector is a quantity that has both length and direction. So if you look at this vector here on the left, this is the vector hg. Remember, you name it with your initial point first, going to your terminal point with that little half arrow. Remember, we can also call this, lowercase little x, for example, and name that vector x, right, with the little arrow on top. Remember, the component form is what we used a lot in transformations when we were talking about translations, and that's the format with these pointy brackets, x comma y, where x is the horizontal change and y is the vertical change, right? So then the component form of vector hg, we would look at basically your rise and your run, right, your slope. So the vertical and horizontal changes, so going from h to g, we went left 1, 2, 3, so that's -3. And the vertical change, we went up 1, 2, 3, 4. So the component form of hg is -3, 4. Sound familiar? Hopefully. So again, this vector hg, oops, it's missing that little half arrow, in component form is -3, 4. You can also look at this vector, and it's also missing that little half arrow, with initial point m and n, and write that in component form by just looking at the differences. Oops. So we can look at the component form of mn being basically the change in x, so from x2 minus x1, right, thinking back to slope, and then y2 minus y1. So the component form of mn would be 10 and -8, because to go from -8 to 2, you went right 10. To go from 1 to 7, we went down 8. All right? Magnitude is the length of our vector. So remember, we had two pieces to it. Direction is our component form, which is where it's going, and length is what we call the magnitude. And how do we calculate the length of a vector? So the notation is going to look like absolute value, but it's actually not the absolute value, so we want to be careful with that. So when you see the vector in those straight vertical brackets, this means we're looking for the magnitude or the length of the vector. How are we going to find that? Well, we want to know how long it is, so what formula do you think we use when we talk about lengths? Distance formula. Okay, so if we take a look at example 2, we're going to draw out this vector and then find the magnitude to the nearest tenth. And this magnitude and direction is going to help us notice how, just giving you a preview, this creates a right triangle. It's going to connect us back to trig when we're looking at specific situations. And oops, I just went all over the place. Okay, so example 2. We're going to draw this vector, and you can pick your initial point to be anywhere. And I always like to pick my initial point to be 0, 0, because it's nice and easy, right? So you can choose your own initial point, and this just means we're going to go left 1, right? Left 1, up 5. So go left 1, up 1, 2, 3, 4, 5. So this is my vector. To find the magnitude, what we want to do is basically look at your distance formula. So since I picked my initial point to be 0, 0, there's my x1, y1. So from there, my terminal point is -1, 5, which is my x2, y2. You guys remember the distance formula? Distance equals the square root of x2 minus x1 squared plus y2 minus y1 squared. Then we're going to go ahead and plug it in and simplify. So I'd like you to go ahead and round to the nearest tenth. So go ahead and finish that off for me, please. Let's go ahead and check your work. Hopefully you got square root 26, which is also approximately 5.1 rounded to the nearest tenth. So that's magnitude. Okay? Direction, I said earlier, is related to component form, but it's not actually just the component form. So the direction itself is the angle a vector makes with a horizontal line. And this is where we're going to use our components and trig to find that specific direction. So if you take a look at example 3, we have our vector 1, 4. We're going to draw it and then find the direction to the nearest degree. And again, you pick your initial point. I always love 0, 0 because it's nice and easy and it's usually centered. Okay? Then we are going to go ahead and go right 1 up 4. So there's the vector. And the question is, where is the direction? Well, remember, the direction is basically that angle of elevation. So this is your horizontal line. So this is the direction that I'm looking for. So that's my x. How am I going to use that to find, or how am I going to use the components to find it? Well, remember that right triangle I pointed out earlier? Use your rise and your run to get that right triangle. So we have a run of 1, a rise of 4. I'm going to redraw this really quick. So here's my right triangle. I'm looking for x. I have 1, I have 4. What is the correct trig ratio? Well, hopefully you got tangent, right? This is opposite. This is adjacent. Tangent x equals 4 over 1. Nice and simple. Tangent x is 4. Remember, to get rid of the tangent, to move it to the other side, we are going to do the arctan, or the inverse tangent function, right, to both sides. So we're left with x equals arctan, or inverse tangent, of 4 to the nearest degree, 76 degrees. All right, so those are the two big concepts for vectors. We're going to go ahead and finish off the back when we're in class. The big thing to make sure we are focusing on when you come back to class is example 4. So we want to know how to do that, because that's going to combine some vectors together. And it's kind of interesting when you think about trajectories. Okay, thanks for listening. Okay, continuing on, let's look at example 4. So now what we want to do is actually kind of work the other direction. So now we're given the direction that's 28 degrees and a magnitude of 12, and now we actually want to break it back down to the components, right? That rise and that run, the x and the y. So what I would do is, remember, your direction is always going to create an angle measure with some horizontal line. So it really doesn't matter if right, you draw this right triangle in whatever orientation, but what matters is this direction, that's 28, is this angle here with the horizontal, right? Because the vector is the hypotenuse, right? This is the vector. So the direction is always the angle the vector makes with a horizontal line, and typically we like to draw that on the x-axis, but it doesn't have to be, right? So it just has to be with a horizontal. Remember, the magnitude is the length, right, of the hypotenuse. So now this vector has a length of 12. So then what we want to do is we want to go backwards and now look for x and y, which are the components of the vector, your overall shift to the left or right, and then the shift up or down. Because remember, these components also tell us a translation from one point to another. So what we want to do is basically go back to our right triangle and trig and think about x and y separately. So what I might do is, and you don't have to draw these triangles separately, but I'm going to look at these pieces individually. So I know this is 12, this is 28 degrees, and this is x. So forgetting about y, right? Going back now to SOHCAHTOA. What would we label x? What would we label 12? And then which trig function would we use? Well, we have x is the adjacent, 12 is the hypotenuse. So what uses adjacent and hypotenuse? Cosine. So cosine of 28 equals x over 12, and then we can go ahead and solve that, right? So similarly, we can go ahead and use a separate triangle, or just label your original triangle with the y now, and think about what we're going to use for y, sine, cosine, or tangent. So again, if this is 28 degrees, oops, and this is a right triangle, otherwise we can't use SOHCAHTOA as it is. This is still 12, but now I'm looking for y, opposite, hypotenuse, sine. So now sine of 28 equals y over 12. So let's go ahead and cross multiply, or just multiply both sides by 12, and let's solve for x and y. There you go. So I just wrote my work down. And then remember, we're looking for the components. So the components mean we want to write component form, which is with those pointed brackets. So we want these little kind of less than greater than signs. So x is 12 cosine 28, y is 12 sine 28. This is the exact value, right? If I had asked you to, let's say, round to the nearest hundredth, then you want to go ahead and put that in the calculator. So 12 cosine 28 turns into approximately 10.60. 12 sine 28 would round to 5.63. But again, if it doesn't ask you to round, go ahead and leave it as the exact value. But if you're rounding, please make sure you round to the correct place value. So that kind of wraps up components, direction, and magnitude. We just have a few more vocabulary words to go through, and then that'll be it for vectors. So equal vectors, parallel vectors, and resultant vectors are the last 3 vocabulary words we really want to go through. So what makes vectors equal? Remember, a vector has both length and direction. So we want to basically have the exact same arrow, which is the exact same length and the exact same orientation. So if you go back to when we talked about transformations, you should be able to shift an arrow onto another, and it should be exactly the same for them to be equal. So it should have the same magnitude, same direction. All right, so what makes equal vectors different from parallel vectors? Well, parallel vectors can actually go opposite directions. So if you imagine equal vectors, for example, these two here, I'm going to draw one in red, and we're going to pretend I draw perfectly. So that red vector x and this orange vector y are the exact same length, and you'll see they're both going up, so they would be equal. So what separates that from parallel? Well, those vectors x and y that I just drew are technically parallel, but if y was going the other direction, these vectors would still be parallel. So it really doesn't matter which direction they're going. What matters is basically that slope, right? That steepness is the same. All right, so again, all they have to have is the same or opposite direction. You'll notice I said nothing about magnitude or length. So that's the other thing that's different about parallel vectors is you can have a shorter arrow and a longer arrow still be parallel. They just wouldn't be equal. So for example, if we look at this vector x, and let's say I draw beautifully and, you know, the slopes are all the same here, I can have a vector y that's going the same slope, but the opposite direction. And let's go ahead and draw in this little z as well. So I can draw in, oh, that's really thick. Let me change that thickness. So we can also have this other mini little vector, and we can call this z. And if it has the same slope as x and y, it doesn't matter that it's so much smaller. They would still be parallel. So we could have x be parallel to y, be also parallel to z. Right, so there's a lot more flexibility with parallel than there is with equal. Equal, it has to be the exact same. They're basically translations of each other. Okay, so look at example 5. With that idea, I'd like you to try to identify the parallel vectors and the equal vectors, but let me actually fix my paper for a moment because my diagram didn't turn out. All right, there you go. So that's much better. So go ahead and try this out. So A, identify the parallel vectors in example 5, and then B, identify the equal vectors. Remember, parallel means they can go either direction, doesn't actually have to be the same length, but equal vectors have to be exactly the same arrow. Okay, so hopefully you saw there's 2 different pairs of parallel vectors. Remember, it's important how you name them. We want to start with the initial point and then end with the terminal point. So you don't want to say this is vector ji, but it's actually ij because it starts at I and points to j. So 2 pairs of parallel vectors, 1 pair of equal vectors. Okay, the last thing we need to talk about is what is a resultant vector. So when you think about a result, that means you have to do something, right, first, and then some new result happens. So a resultant vector is actually very straightforward. All we're going to do is we're going to add vectors. So it's basically what happens when you add 2 different vectors is how we create a resultant vector. Okay, so what does it actually mean to create a resultant vector? How do we add vectors? Well, remember, a vector we represent with an arrow. So what we're actually going to be doing is we're going to be basically putting arrows together. So you're going to create what I like to think about is a path. So let's just draw some vector u. So let's say this is u, and I want to add vector v onto it, and v is going to look like this. Well, how do we do this? Well, to get u plus v, what we're going to basically do, if you want to visualize this, is we start with u. So we're going to start with u, and let's, well, try to make that a little bit more accurate, but let's just pretend I can draw perfectly. So this is the exact same replica as vector u I drew earlier. So that's u. And we want to say, hey, I want to add v onto it. So you want to start off by following u on that arrow to where it ends at its terminal point. And at the terminal point, we're going to go ahead and draw in v. And the resultant vector now just says, okay, now what if I just started at the beginning of u, the initial point of u, but instead of going from u to v in that kind of angle, let's go straight from the initial point of u to the terminal point of v, and that is vector u plus vector v. Okay, so we're just basically making one new vector that starts at the beginning of the first vector and ends at the terminal point of the second vector once we've tacked it onto the original. So it kind of creates a path. So we're seeing that's the shortest distance from the beginning to the end for that path, if that makes sense. So how do we actually do this with numbers? Because, you know, we have components, we have x and y. You literally just add your components. So again, super straightforward. If you look at that, if u has its components are x1, y1, and vector v has its components x2, y2, then u plus v, those two vectors, is just literally x1 plus x2, y1 plus y2, right? So we're just adding our components together to get the resultant vector. So that wraps up this part of the notes. If you have any questions, please let me know.